Hi folks, this is 7.1, Part 1, Graphing Exponential Functions for Algebra 2. As you can tell, this is a little bit more guided notes. So we have the guided notes over here and over here for 7.1 as opposed to my regular permanent marker. Seeing as my permanent marker is just a little bit bigger and these are guided, I'm going to use something a little bit more fun, a little bit cool purple pen here. As you can also tell, my printer did not print out correctly here, and so I had to redraw my table here, and then on the other side as well, I had to kind of add a couple things in. So feel free to go along with your guided notes if you have them. If you are watching this without guided notes, then just make sure that you pause the video often so you can actually get the correct notes that you need. So we're looking at graphing exponential functions, and so our first graph here is function equals 2 to the x power. So first thing we want to do is make our little table right here. And I have an example already written out for you. If x is -3, we're going to have 2 to the -3rd power. Well, any exponent to a negative power is actually, as we know from last unit, is 1 over that number to that exponent as a positive number. So this is 1 over 2 to the 3rd. Which is 1/8. Well, if we were to keep going, we have 2 to the -2nd power equals 1/4. 2 to the -1st power equals 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the 1st power is 2. 2 to the 2nd power is 4. And 2 to the 3rd power is 8. So now that we have our graph filled out, we're going to actually go over here and graph it. Now my grid lines did not print out, but I'm going to probably estimate anyways. Our fractions wouldn't be on grid lines. So we have a -3 right here. We're going to go up about 1/8. Pretty small, but still there. -2 goes up to 1/4. -1 goes up to 1/2. I'm estimating here. 0 is 1. We have 1, 2, 2, 4, and 3, 8. So as you can tell, we are going up exponentially. So if we were to draw this in, it would just keep going and keep going. So we want to also know the domain, range, asymptotes, if there are any, and the y-intercept. So our first thing that we already graphed that y-intercept. So where does it touch the y-axis? 0, 1 is our y-intercept. So I know that's at the bottom right there, but I could add that in. Let's look at our domain. So domain, again, is x values. Well, x values can be all going this way. I check my calculator. I can I can go 2 to the -1,000th power. It's going to be very, very, very small, but it's still going to exist. I can also go 2 to the 1,000th power, and that's going to be very, 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 very large, but it's still going to exist. So our domain is all real numbers. Our range, however, this can get as close to 0 as possible, but doesn't ever actually cross it. So our y value has to be greater than 0. Now, we've talked about asymptotes before, and asymptotes are at what point can that not be? So where can the y value not be? Well, like I said, it gets really close to 0, but it doesn't actually touch it. So y cannot be 0, so there's an asymptote at y equals 0. All right, that's why here y has to be greater than 0, but you note not equal to it because there's an asymptote at that y equals 0. All right, so this is what we call a growth function. Growth function. Let's look at a different type, but very similar function. Here we have function equals 1/2 to the x power. So up here we had a whole number, 2 to the x power. Down here we have a fraction to the x power. This one's already typed out for me, and so 1/2 to the -3rd. Again, anything to the negative We put that on the top to the positive power, and so 2 to the third equals 8th. 8th equals 8. Let's try it again. We have then here 1/2 to the negative second power. This here would equal 2 to the second power, which equals 4. And we keep going. We have 1/2 to the negative first power. This will equal 2. 1/2 to the 0 power. This equals 1. We have 1/2 to the first power. This is going to equal 1/2. 1/2 to the second power, 1/4, and 1/2 to the third power, 1/8. So now that we have our table filled in, again, let's come over here and graph it. Again, I'm not really sure what that's doing there, and my printer was going a little bit crazy. So we have -3. We're going to go up to the 8. Up here is this 4, 5, 6, 7, 8 is right there. So -3 up to the 8th. We're going to put a dot right there. -2. We're going to go up to the 4. -1 up to the 2. 0, 1. 1 is 1/2. 2 is 1/4. 3 is 1/8, and so on. We're going to draw that lovely line in right there. All right, let's look here again. Well, our y-intercept actually stays the same. Our y-intercept is still 0, 1. Here, our domain, again, we can go all the way to the left, all the way to the right. Our domain is still all real numbers. Our range looks pretty similar to our one up above as well. And y is greater than 0. All of our y's are greater than 0. It gets really small, but doesn't fully get to all the way to 0. And finally, our asymptote is still y equals 0. As you can tell from the graphs, if this one was a growth, it grows as you go towards the right as x approaches infinity, y approaches infinity. Here, as x approaches infinity, y approaches, y doesn't approach negative infinity, but y approaches 0. So this is a decay function. Our growth and decay functions kind of look a little bit opposite there, and they are. Now, something else we're going to talk about with this unit here is transformations. And I include transformations even though we've already covered them here. But as I said in another video here, I'm including a lot of things that are also going to be on your SAT. And transformations are definitely going to be on the SAT. So anytime you have an H value, that H value is going to be a horizontal shift. And the H value almost always lies. The horizontal shift almost always lies. And so we have up here our exponential, I guess you can call it parent function here, is a, b. And I'm going to rewrite this in case you really can't see this that well. We have y equals a times b to the x minus h plus k. So this looks very similar to other types of functions we've seen, except for our x minus h this time, instead of being in parentheses, it is in an exponent. So again, if the h is positive, all right, if the h is positive, meaning if you are subtract x minus a positive h, then you are going to go right h units. If h is negative, you're going to go left h units. As is also the case, k is our value on the outside here, and it is a vertical shift. So this is a vertical shift. The k tells the truth, so if k is positive, you go up k units. If k is negative, you go down k units. So the last thing we want to talk about is our a value here. This a value, again, we've talked about this before. A is always the orientation or shape of the function. So orientation or shape. If a is less than 0, it is reflected, the function is reflected from the parent function over the x-axis. So if a is negative, the function's reflected. If a is greater than 1, it is stretched vertically. And if a is between 0 and 1, it is compressed vertically. One last thing I wanted to note here. With this right here, our asymptote is at y equals k. So if there is no k, the asymptote is 0. Just as over here, there's no k value. So that's why our asymptote is 0. It also helps with the range. So that's kind of one way you can tell what goes on with the range and the asymptote. Let's go on and finish here, 7.1 part 2. We're going to be modeling with exponential functions. So I'm going to give you 2 formulas here. On these formulas, we're actually going to be using a, r, and t. And so we're going to have a function of time. So let a of t be the amount after t time period. So t is going to be our time. We're going to use a as our initial amount. And we're going to use r as the percent of increase or decrease. And this is going to be important. This needs to be written as a decimal. So it needs to be written as a decimal. Our growth factor is going to be a of t equals a times 1 plus r to the t power. And our decay factor is going to be a of t equals a times 1 minus r to the t power. So very similar. Again, you see this plus for growth and this minus for decay. That is the differences. So when you're looking at examples, you're actually going to want to identify whether they are growth or decay. My printer left off that important number right there. But example 1 here, we're talking about U.S. Census. So the first U.S. Census conducted in 1790. Here's the original population. This right here would be our A value. Since then, the U.S. population has grown by approximately 2.03% annually. So this is our R value, but we need to make that into a percentage, or I'm sorry, it's a percentage. We need to make that into a decimal to move this back 2 decimal places. So 0.0203 is going to be our R factor right there. It wants us to know what is the approximate population of the U.S. in 2014. So are we dealing with a growth or a decay? Well, if it's grown by that, we're dealing with a growth problem right here. So that means the only thing we have to figure out is our time. Well, time, we want to know what the approximate population of the U.S. was in 2014. So we need to do 2014 minus 1790 when it was originally conducted. And that will give us the time period or the amount of years since the first census was conducted. Well, 2014 minus 1790 is 224. So that is our T value. This is now a plug and chug problem, as I call it. So A of 224 equals, all right, our A value is 3,929,214. And we are going to multiply that by 1. And since it's a growth factor, plus 0.0203. And that's going to be raised to the 224th power. So we're going to want to put this into our calculator. So I'll show you how to do that here. We have 3,929,214 times, well, 1 plus 0.0203 is 1.0203. And we're going to raise that to the 224th power. Sorry, if you can't, sorry, I was a little bit blurry there. And click equal, and we have our A of 224. So our answer is going to be, let's see, this big number right here. I gotta write it out, and then I will, since we can't really have a 0.7 of a person, I'm gonna make this into a 5 right here. And we will box up our answer. So let's go through. There we go, 354,284,615. All right, let's go to our last one here. I apologize, this video is taking a little while, but all right, a large mocha frappe from McDonald's contains 180 milligrams of caffeine. Little fun fact, the recommended dose for teens is 100 milligrams a day. We'll just think about that. However, the average teen can eliminate approximately 12.5%, so eliminate, probably working with a decay function. 12.5% right here, that's R, is going to equal, again, bring the decimal point back, 2.125 of caffeine from their system per hour. Estimate the amount of caffeine in a teenager's body, 3 hours. So 3 hours, that is our time after drinking the large mocha frappe. I'm not even sure if I'm saying that right. I don't drink them, so who knows? So that means our original or our initial amount is 180 milligrams. That is our A right there. So let's plug that in. So we are looking at A of, I think 3. A of 3 equals 180 times 1 minus 0.125. And we're going to raise that to the 3rd power. Again, we're going to come over to our calculator, and we are going to do this time 180 times 1 minus 0.125, all raised to the 3rd power. And again, you use this little caret key right here to get that power up there. Click enter, and you get about 120.6 equals 120.6 milligrams. All right, and there we go, folks.